Today we're going to determine type 1 and type 2 errors and relate confidence intervals to a hypothesis test and for proportions. Remember, the null must be a statement about the value of a parameter for a model, but how do we choose it? Well, we never choose our claim to be the null. Instead, we make what you want to show the alternative hypothesis. In our first example, we have the diabetes drug Avandia was approved to treat type 2 diabetes in 1999, but in 2007, an article in the New England Journal of Medicine raised concerns that the drug might carry an increased risk of heart attack. The study combined results from a number of other separate studies to obtain an overall sample of 4,485 diabetes patients taking Avandia. People with type 2 diabetes are known to have a 20.2% chance of suffering a heart attack within a 7-year period. According to the article's author, Dr. Stephen Neeson, the risk found in the study was equivalent to a 28.9% chance of heart attack over 7 years. The FDA is the government agency responsible for relabeling Avandia to warn of the risk if it is judged to be unsafe. Although these statistical methods they use are more sophisticated, we can get an idea of their reasoning with the tools that we have learned. What null hypothesis and alternative hypothesis about 7-year heart attack risk would you test, and explain why? Let's start out by saying that P is the true proportion of diabetes patients suffering heart attacks in 7 years. That means our null would be P equals 0.202, and our alternative, P is greater than 0.202. Remember, the FDA is concerned if the drug increases the risk of heart attacks is above 20.2%, so a one-sided upper tail test is appropriate. Remember, p-values are conditional probabilities, meaning the probability of the observed statistic given that the null is true. The p-value is not the probability that the null is true. It is not even the probability that the null is true given the data. Remember, the lower the p-value, the more comfortable we feel about our decision to reject the null hypothesis. But the null doesn't get any more false, meaning we can't say if the p-value equals 0.02, this means there's a 2% chance the null is true. So continuing with our Avandia, increased risk of heart attack was raised by a study of the New England Journal of Medicine. Remember, the study estimated the 7-year risk of heart attack to be 28.9% and reported a p-value of 0.03 for a test of whether this risk was higher than the baseline 7-year risk of 20.2%. An earlier study had estimated the 7-year risk to be 26.9% and reported p-value of 0.27. Why did the researchers in the ADOPT study not express alarm about the increased risk that they had seen? So in this example, we have a p-value of 0.27. It means the heart attack rate is at least as high as the observed could be expected in 27% of similar experiments. This isn't enough evidence to reject the null. The ADOPT study was not convincing. Sometimes we need to make a firm decision about whether or not to reject the null. We reject the null if our statistic is considered rare, meaning a small p-value. We can define the rare event by setting a threshold for our p-value. That threshold is the alpha level, denoted as the Greek letter alpha. Looks like almost like a Christian fish. If our p-value is less than the threshold, we reject the null. We call such results statistically significant. Common alpha levels are 10%, 5%, and 1%. The alpha level is the significance level. You must choose your alpha level before performing your test. If the p-value falls above, then you fail to reject the null. Do not ever say accept the null. If you do, you will be extremely sad. Otherwise, you can be accused of cheating and making alpha fit the data if you don't state your alpha level before you do your test. Because confidence intervals are two-sided, they correspond to a two-sided test. A confidence interval with level confidence C% corresponding to a two-sided hypothesis test has an alpha level of 100 minus the confidence level. A confidence interval with a confidence level of C% corresponding to a one-sided hypothesis test has an alpha level of 1/2 minus 100 minus C%. Back to Avandia. The baseline 7-year risk of heart attacks for diabetes is 20.2%. In the journal, it reported a 95% confidence interval equivalent to 20.8% to 40% for the risk among patients taking the diabetes drug Avandia. What did this confidence interval suggest to the FDA about the safety of the drug? Remember when we did our 2 confidence level assignments, we compared the end of the confidence interval and the beginning of the confidence interval to our parameter or sample proportion. Okay, so we can say the FDA could be 95% confident that the interval from 20.8% to 40% included the true risk of heart attack for diabetes patients taking Avandia. Because the lower limit of this interval is higher than the baseline risk of 20.2%, there was evidence of an increased risk. So what we're saying here is the 20.2% doesn't fit into the boundaries of the confidence interval, and because of that, we have evidence to suggest it is really higher. 20.2% is less than 20.8%. In our next example, we have an experiment to test the fairness of a roulette wheel. It gives a z-score of 0.62. What would you conclude? So first of all, we're determining the fairness of the roulette wheel. So that means we will have a two-tailed test. So I would take the z-score, 0.62. I would look it up on my chart. Because it would be a right shade on the positive side, we're going to subtract that answer from 1, and then we will multiply it by 2. So when we do so, we should get a p-value of about 0.535. And we would fail to reject a null because 0.535 is greater than 5%. And we would say the experiment shows no evidence that the wheel is unfair. For number 2, we have a bank that wondered if you could get more customers to make payments on delinquent balances by sending them a DVD, urging them to set up a payment plan. Well, the bank just got back the results on their test of this strategy. A 90% confidence interval for the success rate was from 29% to 45%. The old send a letter method had worked 30% of the time. Can you reject the null hypothesis that the proportion is still 30% with an alpha of 5%? So with an alpha of 5%, we fail to reject a null because 0.3 is included in our confidence interval. It is possible that sending the DVD is no more effective than just sending a letter. Now let's look at number 3. It says, given the confidence interval the bank found in their trial of DVDs, what would you recommend they do? Should they scrap the DVD strategy? The bank could do another trial with a narrower confidence interval with a larger sample size. Okay? And if I do a narrower confidence interval, I become more precise because the range of it is smaller. If I use a larger sample size, my standard deviation also becomes smaller. In our last example, we have teens are at the greatest risk of being killed or injured in traffic crashes. According to the National Highway Traffic Safety Administration, 65% of young people killed weren't wearing their seatbelts. Okay, so that 65% is probably important, so we're going to underline it. In 2001, a total of 3,322 teens were killed in motor vehicle crashes, an average of 9 teens per day. Because many of these deaths could have easily been prevented, several states have begun a click it or ticket campaign in which increased enforcement and publicity have resulted in significantly higher seatbelt use. Overall, the use in Massachusetts quickly increased from 51% in 2002 to 64.8% in 2006, with a goal of surpassing the national average of 82%. Recently, a local newspaper reported that a roadblock resulted in 23 tickets to drivers who were unbelted out of 134 stopped for inspection. Does this provide evidence that the goal of over 82% compliance was met? We're going to use a confidence interval to test this hypothesis. For our state step, we're going to have P as the true proportion of teens wearing seatbelts. Next is our plan. For our plan step, we're going to use a 1 proportion z interval, a random. It is not stated in this problem the sample was random, so for now we're just going to assume the drivers that are stopped are representative of all teen drivers. 134 drivers is less than 10% of all teen drivers. Our success fail, we're given in this situation, so 134 minus 23 is 111. Those are our successes of both the teens, and NQ would be 23. Those would be the citations issued. Both NP hat and NQ hat are at least 10, so the model is approximately normal. Remember, for the success fail condition, because we are trying to estimate the population proportion, we need to have hats over our large enough success fail. For our do step, we're going to take what happened in the sample. So we had 111 of the 134 teens wearing seatbelts, plus minus. Now, if I want a 5% significance level in this thinking bubble over here, note that if I want 5% on the lower end for my rejection region, then that means I have to have 5% on the upper end, which make this a 90% confidence interval. Remember, the z star value for a 90% confidence interval is 1.645. And then we find our standard error. We would do the square root of our successes, 111 over 134, times 23 over 134, and then divide the entire result by 134. We should get approximately 0.775 to 0.882. So for our conclude, we're going to say we are 90% confident that the true proportion of teens wearing seatbelts is between 0.775 and 0.882. Since 82% is included in the interval, we do not have enough evidence to suggest the campaign was successful and more than 82% of teens wear their seatbelts. And that takes care of this problem. Yay, we're finished. Time for practice. The end.